Sound is everywhere, right? It's all around us all the time. But have you ever really stopped to think about what it is? What's actually happening? It's not just noise, it's a physical journey. And today, we're going to follow that journey right from the very beginning.
So let's just ask it straight up. What is sound? Like on a fundamental physical level. We're not talking about your favorite song or that annoying car alarm, but what is the stuff that makes those things possible?
Because here's the thing, sound isn't just something that magically appears in our ears. No, it's an actual physical event. It's a journey of energy that has to travel from a source to our ears. And to really get it, we have to go back to where it all begins.
And that beginning, the birthplace of every single sound you have ever heard, well, it all comes down to one simple thing: vibration.
That's it. It's honestly that simple. From the quietest little whisper to a huge booming explosion, every single sound in the universe starts with an object doing a little shake, a wobble, a quiver, whatever you want to call it. And that rapid back and forth movement is what we officially call a vibration. Just think of a guitar string right after you pluck it. You can see it shimmering, right? Or a big bell after it's been rung. That movement you can actually see, that is the sound being born. So it really happens in these 3 simple steps. First, something gets disturbed. It gets hit or plucked or air is blown through it. Second, that disturbance makes it move back and forth super fast. And third, that movement, that vibration, is what kicks the whole process off. But of course, the story doesn't end there. So, we've got a vibration. That's awesome. But that's just the start of the adventure, A vibration at the source is one thing. But how does it get from, say, a guitar string all the way across the room to your ears? Well, this is where that little shake transforms into a wave. That energy has to travel. It can't just sit there. The vibration starts pushing on whatever's around it, and usually that's the air. It passes its motion along, almost like a baton in a relay race.
Okay, here's a great way to think about it. Imagine you're standing in a really long, crowded line. If you give the person in front of you a little nudge, they're going to bump into the next person, who bumps into the next, and so on, right? The nudge travels all the way down the line. But here's the key. Each person pretty much stays in their own spot. That's exactly what air molecules do. They just bump into their neighbors and pass the energy along.
So let's make this crystal clear, because this is the whole shebang. The vibration is the cause, is the original shake, the start of it all. The sound wave is the effect. It's the pattern of that shake as it travels through something, like the air. So vibration is the start. The wave tells the story of its journey.
All right, that's the theory. But how does this play out in the real world? Let's take a look at a perfect, everyday example that puts all of this together.
We've got them everywhere. In our phones, our TVs, our cars. And what is a loudspeaker really? It's just a machine that has absolutely perfected the art of turning electricity into physical vibrations. Let's break it down. First, an electrical signal, your music, a podcast, whatever, is sent to the speaker. Second, that electricity makes a part of the speaker called a cone move back and forth, vibrating with incredible precision. Third, and this should sound familiar, that moving cone pushes and pulls on the air molecules right in front of it. And finally, that pushing and pulling creates the sound wave, that traveling nudge that makes its journey through the air all the way to you. So when you really get down to it, that fancy, expensive sound system you've got, it's just a highly sophisticated vibration-making machine. That's its whole job, to create very specific shakes that become waves that become the music you love. Pretty cool, right? So let's do a quick recap. What's the bottom line? Number 1, every single sound starts with a vibration. Number 2, that vibration travels in the form of a wave. And number 3, these waves are what carry sound energy through a medium, like air, to your ears. From a simple shake to a traveling wave, to what you're hearing right now. And I'll leave you with one last thing to chew on. If all sound is motion, this constant energetic vibration, then what does that make silence? Is it just perfect stillness? And in a world as noisy as ours, do you think true silence is even possible anymore? Something to think about. You're surrounded by sound, right? It's literally everywhere. It's the first thing you hear in the morning, the last thing at night. We know it, we can feel it, but what if we could actually see it? What does sound really look like? Well, that's exactly what we're going to figure out. Really think about it. We all know a whisper and a shout are opposites, but if you had to sit down and draw them, what would be the difference? Over the next couple of minutes, we are going to turn the everyday sounds we all hear into something we can actually see.
All right, so before we can start drawing anything, we need to get a handle on a couple of basic concepts. See, when we talk about any sound, we're really talking about two key things that you already understand, even if you don't use these exact words. It's volume and it's pitch.
First up, let's talk about volume. This one is all about pure power. It's the difference between the roar of a jet engine and, the quiet little tap of a key on your keyboard. It's all about intensity, how loud or how soft a sound is.
Now, the other side of that coin is pitch. This isn't about power at all. It's all about tone. Think about the deep rumbling boom of a bass drum compared to the super high, sharp sound of a whistle. That highness or lowness, that's its pitch.
So we've got our two main ingredients, volume and pitch. But how in the world do we turn those ideas into an actual picture? This is where science gives us this really cool tool that, you guessed it, makes the invisible visible.
And here it is. This squiggly line is called a wave trace diagram, and it's the key to everything. I know it looks pretty simple, but it holds all the visual information we need to actually see sound. So let's break it down.
Okay, first things first, let's tackle volume. How do we take that feeling of loudness and translate it into a shape on our diagram? Well, it turns out there's a very direct connection.
Let's go back to our whisper versus our shout. If you were to draw both of them using that wave diagram we just saw, what do you think the single biggest difference would look like?
The answer? It's all about height. Seriously, the scientific term is amplitude, but the idea is incredibly simple. The taller the wave, the louder the sound. A quiet whisper makes a short, shallow wave. A powerful shout, that creates a tall, towering one. That's it. Simple as that.
Okay, so we've totally cracked the code for volume. It's all about height. But what about pitch? How do we visualize the difference between that low bass note and the high flute note? Well, with pitch, it's not about the height of the wave anymore. Instead, what you want to look at is how crowded or how spread out the waves are. This is the visual key to understanding pitch.
The scientific term for this is frequency. Think of it like this. A low-pitch sound, like a bass drum, creates these kind of lazy, spread-out waves. That's low frequency. A high-pitched sound, like a flute, creates waves that are rapid and bunch tightly together. That's high frequency. So, the faster the waves, the higher the pitch.
We even have a special unit to measure this, hertz, which you'll usually just see written as Hz. And it's way simpler than it sounds. 1 hertz just means one wave cycle passes by in 1 second. So a high hertz number just means a ton of waves are packed together, which, as we now know, means it's a very high-pitched sound. So let's put it all together. Our everyday experience of volume is really a measure of amplitude, which we see as wave height. And our experience of pitch is just a measure of frequency, which we see as wave density. This little chart is basically the Rosetta Stone for seeing sound.
So, to wrap this all up, let's take everything we've just learned. We now know that a loud, high-pitched scream would be a very tall wave, with its peaks and valleys packed super tightly together. Which leaves us with one final fascinating question to ponder. Using these same rules, what does silence look like? I'll let you think about that one. Thanks for joining me.
You know, from the jolt of your alarm clock in the morning to the low hum of traffic at night, our whole world is just painted with sound. But have you ever really stopped to think about what sound actually is? It's not magic, it's pure physics. And behind every single sound you've ever heard, there's this incredible, invisible story happening. So let's break it down.
So let's just dive right in. What is sound? I mean, really. Imagine you pluck a guitar string. You see it vibrate, and a split second later, you hear the note. So what happened in that tiny gap of time? What was it that actually traveled across the room and into your ear? Well, it turns out it's a surprisingly elegant, invisible dance of energy.
Okay, so the secret to every sound in the entire universe, from the quietest whisper to a massive thunderclap, it all starts with one single thing: vibration. That's it. It's the physical spark that kicks off the whole shebang. So a vibration is just what it sounds like, a super rapid back-and-forth movement. When you clap your hands, you're not just making a noise, you are literally violently shoving air molecules out of the way. When a big bell rings, the metal itself is physically shuddering back and forth, and that creates this ripple in the air all around it. Every single sound has to start with some kind of physical disturbance like this.
And this is the really cool part.
how that disturbance actually travels. The best way to think of it is like a long line of dominoes. The first domino doesn't magically jump to the end of the line, right? Of course not. It just tips over and passes its energy along to the next one. And that's exactly what particles in the air do. They bump into their neighbors, which bump into their neighbors, passing the energy along in this perfect chain reaction, all while staying more or less in the same spot. All right, now here's a common mix-up I want to clear up. When we think of a wave, most of us picture, an ocean wave with those classic crests and troughs moving up and down. That's called a transverse wave. But sound is different. It's what's called a longitudinal wave. So instead of moving up and down, the particles are actually pushed forwards and backwards in the exact same direction the wave is traveling. This creates these little zones where the particles are all bunched up in high pressure and other zones where they're all stretched out in low pressure.
So, we've got a vibration kicking off a chain reaction. But what exactly is that chain reaction traveling through? Let's follow that sound wave on its journey from point A to point B.
Right. So here's the catch. Sound is a little bit needy. It can't travel through nothing. It has to have a medium, some kind of stuff with particles in it, to carry the vibration. That could be a gas, like the air we're breathing, a liquid, like water, or even a solid, like a concrete wall. This is the classic reason why there's no sound in space, right? In space, no one can hear you scream. It's a vacuum. There are no particles, so there are no dominoes to fall.
So let's just put all the pieces together real quick. It all starts with a source that vibrates. That vibration makes nearby particles collide with each other. That collision starts a chain reaction, transferring that energy down the line particle by particle. And that moving wave of energy, that is the sound we hear. It's this beautiful, invisible process that's happening all around us, all the time.
Okay, if the domino analogy didn't quite click for you, this one will. The absolute best way to visualize this is with a slinky. You know how if you push one end, you don't send the whole spring flying? Instead, you send this little pulse of bunched up coils zipping down its length? That pulse is a perfect slow-motion visual of a sound wave. Those bunched up parts are what scientists call compressions, and the stretched out parts in between, those are called rarefactions.
We know sound travels through solids, liquids, and gases. But does it travel at the same speed in all of them? Oh, not even close. So, you know what? Let's stage a race.
Here's the question for you. In which of these three mediums does sound win the race? Is it going to be fastest in the air we breathe, the water we swim in, or through a solid block of steel? Go ahead, take a guess before we show the results.
And the results are in. And wow, just look at that difference. It's not even a fair race, is it? Sound is kind of sluggish in air. It's way faster in water, but it absolutely screams through solids. So clearly, the medium doesn't just carry the sound, it completely changes the rules of the game.
So what's going on here? Why this massive speed difference? Well, it all comes down to one thing: density. It's about how close those little particles are to each other. In air, the particles are kind of lazy and spread way out, so it takes a while for the energy to get passed from one to the next. But in a solid, they're packed in there shoulder to shoulder. The moment one vibrates, its neighbor feels it. The energy transfer is pretty much instantaneous.
So let's make it official and declare our winner, solids, by a landslide. You know, this is exactly why you can hear a train coming by putting your ear to the track long before you can actually hear it through the air. That vibration travels so much more efficiently through the solid steel rail because those particles are just so close together.
So what's the big picture here? Let's just recap. We've seen that every sound is just a vibration. That vibration sends a push-pull, longitudinal wave of energy through a medium. It absolutely needs that medium, solid, liquid, or gas, to travel. And finally, sound travels fastest through solids and slowest through gases, all because of how tightly packed those particles are.
Which, leaves us with one final, kind of mind-bending thought. We now know that because space is a vacuum, the most colossal, violent events in the universe, stars exploding, galaxies colliding, are all happening in absolute, complete silence. It makes you wonder, if sound could travel through the cosmos, what kind of incredible, maybe terrifying symphony would we be hearing right now? Something to think about. Thanks for joining me for this explainer.